So the extreme value theorem is an existence theorem, much like the mean value theorem was an existence theorem. It just simply says something exists. So the extreme value theorem says if f of x is continuous on a closed interval from a to b, then f of x has both an absolute minimum and maximum on the interval. So what you saw on a previous slide were some examples where it couldn't and it didn't. But let's imagine that I'm going from this point to this point. I have to create an absolute max and an absolute min for doing that. If I actually just go straight across, then the height of this would be the max and the height of this would be the min. If I do anything else, the same thing is going to happen. So if I go up, I must come back down. Now keep in mind it says it's continuous, so I can't break it up in any way, but this point right here, the height of that would be my max, and then the height of this point down here would be my min. I always get questions like, what if I go straight across? Well, I still have an absolute max and an absolute min. It's just that it's the same number, which brings up the point like, well, what if it happens multiple times? All right, so say this is the same height as this, and this is the same height as this. Well, you're giving y values, not x values in this location. So you're still going to have one answer for both the absolute max and the absolute min. It's the highest and lowest points that the graph can reach. All right, the candidates test is how we actually justify, and it also gives you a structure for finding them analytically. So the first thing you're going to do is figure out where the candidates are. So the candidates for absolute maxes and min are the x values of the critical numbers and the endpoint. So you can imagine, let me do this. All right, so here's where the min is. That's at an endpoint. Here's where the max is. That's at an endpoint. All right, so the min and the max happen there. Well, what happens if my graph goes above an endpoint? Remember that this is continuous on a closed interval. So my max would be right there, but that's at a critical number because the slope there is 0. And then here, that's at an endpoint. So you actually find the critical numbers first. That's step one. And you'll just do some work analytically. And then the second step is you're actually going to start the justification right then. So it starts with the sentence. Absolute extrema can take place at critical numbers, or you could say a relative max or min, depending on the question. And then you would list them. So you would say x equals this, 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 or endpoints, and then list those. So you're naming the candidates, which are the x values. And you are saying why they are candidates, which is they're either critical numbers, locations for relative maxes and mins, or endpoints. Now, the reason I say you can actually use, instead of just saying critical numbers, is a relative max or a min, is that it depends on what they ask for. If it asks for an absolute max and only at an absolute max, then you could say it's going to take place either at a relative max or at an endpoint. So you could specify an absolute min could take place at a relative min or an endpoint. Now, analytically, I would not specify. I would stick with critical numbers because if you wanted to decide if they are maxes or mins, you're doing more work. All right, so you don't want to do that. But graphically, if I had the graph of the first derivative, it's easy to tell if it's a relative max or a min. If that's my axis and it goes through like this, and this is on the graph of f prime, then that will be the location of a relative max because f prime is changing from positive to negative. So if it only asks about relative maxima, and let's say my graph turned and came back up, I do not have to list that point because that's a relative min, and there's no way an absolute max can happen at a relative min. All right, so you would name the candidates and why they're candidates in the sentence, and then you're going to actually do your work. So you're going to evaluate f of x, not f prime, but f of x at each one of those. You are looking for the y values. So you literally just plug them into the original function. I do it in order, from the left endpoint to the right endpoint, and then the critical numbers that happen to be between, because you can get critical numbers that are not in your interval. And if that's the case, you would ignore them. That's not where we're supposed to be looking. The very last step is you label which one is your max and which one is your min. Now, what you need to remember is that these are the y values. I'm not asking the x value when I'm asking for the absolute extreme. I'm asking what is the height. So basically, you're finding the range. The minimum is the lowest value of the range, and the maximum is the highest value of the range. And this is of the original function.